Welcome to a refresher lesson for exponential and logarithmic functions solving equations. This video corresponds to the examples on a worksheet packet that can be found at my Teachers Pay Teachers store. In this video, I will explain the skills and steps necessary to complete all of the examples on the worksheet. Please feel free to skip around to engage in the concepts with which you would like some help. So as we consider solving exponential and logarithmic functions, we first want to consider this one-to-one property. And the one-to-one property works for both exponential equations or functions and logarithmic equations and functions. And it basically says that if you have in the exponential equation, for example, if you have a b value, some base, that is being taken to an m exponent, which could be any algebraic expression. So it could be a number, it could be, x plus 3, it could be x squared, whatever. If you take b to that power and you say that that's equal to the same base b taken to an n power, which is also just some algebraic expression, then it follows that m and n would have to be equal to each other. So if the b's taken to the powers of m and m are equal, then the m and the n have to be equal. Similarly, with logarithmic functions, if you are taking a log of some m expression and the log of some n expression, and again with b's that are the same value here on both logs, then again it follows that the m and the n expressions would have to be equal to each other in order for the logs of each of those to be equal to each other. Okay, so when you are solving equations, for example, solving an exponential equation, one of the first things you want to look at is what are the bases that I have in my exponential expressions, especially if you have an exponential equal to an exponential. If you have something like this, where you can see we already have the same base of 5 in both sides, then we can very simply say that, okay, well then this power of 2x minus 3 has to equal this power of 3x plus 7. And now instead of trying to actually solve an exponential equation, we're really just solving a linear equation. But again, this only works if the bases are the same. So now I can subtract my 2x from both sides. That's going to give me a negative 3 equal to x plus 7. I'll subtract my 7 from both sides, and we get an x equal to negative 10. Now, it's always a good idea to put your solutions back into your original equation to make sure that they work. Although with exponential equations, there's not as much concern about them working, because remember back when we were graphing in our previous lesson, exponential functions have a domain of all real numbers. So you can basically use any value for x and it should work. So as long as you've worked carefully, you could always substitute the x back in to check for your accuracy. But in terms of having any kind of extraneous solution or anything like that, you usually are not going to get that with an exponential equation. Now let's take a look at another example. Here we're looking at 4 to the x power being equal to 1/8 to the x plus 1. Now, on initial inspection, it looks like we do not have the same base in each of our exponential expressions on each side of the equation. However, both 4 and 1/8 can be rewritten as base 2 expressions. So for example, the 4 here, we could rewrite as 2 squared. And the 1/8 here, we could rewrite as 2 to the -3 power. So by doing that, by looking at those and realizing that they can be rewritten as base 2 powers, we can then use our one-to-one property. Now, before we do that, we want to do a little bit of simplifying. We want to remember that a power raised to another power means we're going to multiply the exponents. So this is going to simplify to a 2 to the 2x. And this side is going to simplify to 2. And then this -3 is going to distribute through our x plus 1. So we're going to have a -3x minus 3 for our exponent. Now we have the same bases. Now we can set our exponents equal to each other and then solve that equation. So I'll add my 3x over to get 5x. I'll still have -3 on this side. Divide both sides by 5, which is the same as a -0.6. And again, you can put that into the equation. You could check it on a calculator to make sure that that is indeed the correct answer. But in terms of having any extraneous solutions, not going to be an issue with exponential equations. Now, what happens when you cannot rewrite your exponentials with the same base? So let's say, for example, I have 3 to the 2x on the left side, and I'm equal to 15 on the right side. There is no way to rewrite 15 as the power of 3. And so we need a different method when we're not able to rewrite using same bases and using our one-to-one property. And so this is where the idea of exponential functions and logarithmic functions being inverse functions of each other comes in. So because we are using an exponential equation, that's what we're trying to solve, we're going to use a logarithm to sort of cancel the exponential part. Now, when you do this, you want to pick what I call a strategic log. And what that means is going to depend a little bit on what you have available to you for your calculator. Okay, so if you have a calculator that allows you to choose the base of your log, then a strategic log is going to be a log that matches the base of your exponent. And just like any other inverse operation, like dividing or square rooting or anything like that, we're going to do this to both sides. So I'm going to take the log with a base of 3 of the left side, which is 3 to the 2x, and I'm going to take the same log with a base of 3 to the right side, which was 15. Now, the reason I'm choosing that is because from our properties and operations lesson, we know that if the base on our log and the base on our exponent match, they cancel each other out. And so on our left side, we're left with just a 2x equal to the log base 3 of 15. And now to isolate the x, we are going to divide both sides by 2. Okay, so if you have a calculator that will allow you to do that, or if you're using Desmos, you can go onto Desmos, you can go here to the functions, and you're going to scroll to the calculus set right there, and you see you've got a log with a tiny little a there. Whoops, hit the wrong one, sorry. There we go, try that again. Down to calculus. All right, so there's the log base a, and you can see the cursor is blinking in the base spot. So we wanted a log base 3. And then we're going to get into the parentheses and we're going to put the 15. We'll close those parentheses. And then we're going to divide everything by 2. And you can see, because you didn't set it up as y equals something, you're not getting a graph of this, you're just getting the answer, which is 1.232. We usually go about 3 decimal places with these answers. So 1.232 is what we would want for our answer. So approximately 1.232. Now, if you have a calculator that does not allow you to put in your own base, so you really only have natural or common logs to choose from, then you can do that to both sides. So let's say for a minute that we decide to take the natural log of both sides of the equation. Okay. Now, based on our laws of logarithms, we know that this exponent can come down in front. So this will become a 2x times ln 3, and this will become ln 15. And then we're going to divide by the 2 and the ln 3 to get x by itself. So ln 15 is going to be divided by 2 ln 3. And if you saw the properties and operations video, you know that this ln 15 divided by ln 3 is really just the change of base formula for the log base 3 of 15. Okay, so you could also do it this way and then use your change of base formula if you need to. Okay. But now we're looking at natural log of 15 over 2 times the natural log of 3. So if I go to a calculator where those are the only options I have, I'm going to take the 15 natural log, and then I'm going to divide that by, in parentheses, 2 times 3 natural log, close my parentheses, and that equals the same answer, 1.232 to 3 places. Okay, so either way will work. And again, you need to be strategic based on what you have available to you to be able to calculate your final answer. Okay, let's take a look at another example. Now, in this example, you can see we have a lot going on. We've got 3 times e to the x minus 2 power plus 5 equal to 14. So before we can use the logarithm of both sides, we need to get this exponential piece isolated. So this e to the x minus 2 power needs to get isolated. So we're going to subtract 5 from both sides first, using normal inverse operation. So that's 3e to the x minus 2 equal to 9. Then we'll divide both sides by the 3 because that 3 is not part of the base. We don't have parentheses around the 3 and the e, so 3 is not part of the base. So we can divide both sides by 3 to get e to the x minus 2 equal to 3. And then because our base is in e, we will want to use natural log in this case. That's our strategic pick. We will take the natural log of both sides. And so here the natural log and the e basically cancel each other out. So we have an x minus 2 equal to natural log of 3. And then we'll add the 2 to both sides to isolate the x. And so now I can go to any of my calculators. I'll go back to our basic calculator. And I'm going to be taking See, what was that again? The natural log of 3 plus 2. Okay, so 3 natural log plus 2 equals 3.099. I would round that 8 up to a 9 because of the 6. So 3.099 is our approximate answer. Okay. Now, if we move on to logarithmic equations, again, one of the first things you can look for is whether you can use the one-to-one property. So if it's something like this, where we have the log of x squared equal to the log of x plus 6, it's pretty straightforward that we can take this x squared, set it equal to that x plus 6, and then solve that equation to see what our possible solutions would be. So I'm going to subtract the x and the 6 to get this equal to 0, since we're now dealing with a quadratic equation. Then I'm going to factor x minus 3 times x plus 2. And that means our x values could be a 3 or a negative 2. Now, with logarithmic equations, it is super important that you check your answers. Because, again, if you remember when we were graphing logarithmic equations, logarithmic functions have a restricted domain. You are only allowed to use positive values in logarithms. Now, be careful when I say that. That does not mean that x has to always be positive. It means that whatever it is we're taking the log of, so here the x squared and the x plus 6, that part has to be positive. So if I'm going to check these, for x equals 3, I'd be looking at the log of 3 squared being equal to the log of 3 plus 6. This is going to be the log of 9, so that's positive, that's okay. This is also going to be the log of 9, so that's positive, that's okay. And so 3 checks out. Then I'm going to check when x is negative 2. So the log of negative 2 squared being equal to the log of negative 2 plus 6. Negative 2 squared is going to be the log of 4. Negative 2 plus 6 will also give me the log of 4. So again, we are taking the log of a positive value on both sides, and it is the same value. So even though the 2 is negative, when I put it into the original equation, I'm still okay because I'm still taking the log of positive values. So both my positive 3 and my negative 2 will indeed work in this case. Okay. Now, if we look at another example here, this does not initially look like it's going to fit the one-to-one property because I have 2 natural logs being subtracted on the left side equal to a single natural log on the right side. But we know from our properties that that subtraction means I can combine these natural logs into x minus 2 divided by x. And so when I combine those 2 natural logs on the left side, then I have an equation that fits the one-to-one property. So I can look at x minus 2 over x being equal to 3. I will multiply the x on both sides. Then I will solve this. So I will, whoops, sorry. So we're going to subtract the x, get a negative 2 equal to 2x, and x is going to equal negative 1. Now, when I go to check this one, I'm looking at the natural log of negative 1 minus 2 minus the natural log of -1 equal to the natural log of 3. Now, even if that does work out, our issue is we end up with a natural log of -3 here, and we already have a natural log of -1 here, and those cannot be evaluated. Those are not possible. So as long as you get any part of the equation that cannot be evaluated, you cannot use that value for a solution. And since -1 was the only x value we came up with, that means there is no solution to this equation. Okay, so with logarithmic equations, one-to-one property is usually a single log equal to a single log. But what happens when that's not the case? You only end up with one log on one side, and you need to be able to solve that type of equation. Well, again, your first step is going to be to isolate that logarithmic expression. So this log base 2 of x is what we want to get isolated. So we are going to subtract that 4 first, and then we'll go ahead and divide by the 3 so that we get the log base 2 of x all by itself. And 9 divided by 3 is 3. And then again, we're going to use this idea of exponentials and logarithms being inverse functions of each other. And really, this goes back to just what the definition of logarithm is from our properties and operations lesson. So we can take a logarithmic equation and we can rewrite it in an exponential form. So taking the log base 2 of x equal to 3, we can rewrite that as being 2 cubed equals x. And so that means our x is supposed to equal 8. And if we check that and put it back into our original equation, 3 log base 2 of 8 plus 4 equals 13. So I am taking the log of a positive here, and indeed log base 2 of 8 is equal to 3, so it does work out to the correct answer. So this does work, and x equals 8 is our solution. Okay, so if we can't set up a one-to-one, then we're going to rely on the definition and rewriting our logarithm into exponential form as the way to solve our problem. Let's look at one more example. Here I have 2 logs, but they're both on the same side of the equation. Now, I could attempt to move one of them over to the other side, but that still would not fit the one-to-one property because of that 2 that's there. I would not end up with just a log equal to a log. So instead, I'm going to go back to thinking about the laws of logarithms again, realizing that this addition sign between the 2 logs on the left side means that I can rewrite this and combine it as the product of x and 4x. And so I'm looking at the log of 4x squared being equal to 2. Okay, now this log, because there wasn't anything written here as a subscript, means it's a common log, and automatically that means that it's 10. So when I go to rewrite this in exponential form, I'm going to be taking 10 to the second power and setting it equal to my 4x squared. So that means it's 100 equal to 4x squared. Divide both sides by 4, we get 25 equals x squared. And when I take the square root, because I'm solving, I want to consider both the positive and the -5 as possible solutions. Now, when I check, if I put the positive 5 in, I'm looking at a log of 5 plus a log of 20, 4 times 5, equal to 2. That seems okay. We're taking the logs of positives. We could multiply the 5 and the 20 together if we really wanted to work it out, or we could just put it into our calculator, take the log of 5 plus the log of 20, and we get the 2. So it does check out. Okay. Now, if I'm going to use the negative 5, sorry, going to use the negative 5, then I would have a log of negative 5 plus a log of negative 20 equal to 2. Now, even though I would be multiplying those two numbers together potentially to get a log of 100, which is equal to 2, the fact that I'm taking the logs of negatives in both of these is a problem and cannot be evaluated individually. So my final answer is only going to be the x equals positive 5. The negative 5 is not a reasonable answer. It is an extraneous solution. Okay, so again, with exponential equations, you don't have to worry so much about those extraneous solutions because exponential functions have a domain of all real numbers. So any value of x will work. But with your logarithmic equations, because you have a restricted domain, you have to check your solutions to make sure they really are going to work in your equations. All right, well, I hope you found this lesson helpful. If you would like to see other concepts that you need to refresh or review, please check out my Gordon Global Math page on YouTube. Videos covering Algebra 2 and pre-calculus concepts will be added throughout the spring of 2025. Thanks for watching.